How's it going, ladies and gentlemen? It's Johnny here again, taking a look at 16.7 problems, talking about weak bases. We want to know what it means to be weak, what makes a weak base weak, and we want to be able to use the KB to determine pH and concentration and vice versa. We want to be able to convert between those two. So let's start with number one. All right, it says, which of the conjugate bases below is the strongest base? All right, well, they're giving us Kas for the acid. So if we want the strongest conjugate base, we want it to have the weakest acid. Right, strong acid would give you a weak conjugate base, and a weak acid would give you a strong conjugate base. So if we're looking at these Kas, weakest acid is going to be the smallest Ka. So you got to remember, negative exponents means, all right, bigger the negative, the smaller it is. So that gets rid of these two options. So now we're looking at just these two. We got 1.8 and 6.3. Well, which one is the smallest? It's HOAC. So this is the weakest acid, and what would its conjugate base be? A. Right, because that's the acid without the base, the acid without the H+. All right, number two. Which of the conjugate acids below is the strongest acid? Again, they're giving us Kb, and we are looking at the conjugate acid. So if we want strongest acid, we want the weakest base. So weakest base is going to have the smallest Kb. So we, all right, well, -4 is bigger than -7, so I can get rid of these two options. 1.8 versus 3.3. 1.8 is smaller. So this is a weaker base, but they want the conjugate acid. So it'll be H2S, which would be choice C. All right, number three, doing some math. The pH of 0.55 molar aqueous solution of ammonia, NH3, at 25 degrees Celsius is 11.5. What is the value of Kb for NH3? So it's saying we got NH3 being put into water, which is a liquid, gives us NH4 plus OH minus, and wants to know what the Kb is. So what we're really trying to figure out, well, the Kb expression is the NH4 plus concentration times the OH minus concentration all over the NH3 concentration. All right. So the first thing that we're going to need to do is we're going to need to figure out, well, if they gave us a pH, they gave us a molarity, right? And yeah, no, they gave us pH over here. So we can use that pH to figure out, well, how much OH minus do we have? So you got to remember, well, pH is equal to 14 minus the POH, right? Or, little algebra, POH equals 14 minus the pH. And if you don't understand why I'm using this formula, in a second you will. So we plug that in so that we can get the POH, which is, what, 2.5? Can you do that? Yeah. So the POH is 2.5, which is equal to the negative log of the OH concentration. So now we can figure out the OH concentration. So OH is going to equal 10 to the negative 2.5. And that's just algebra from here. And I get an OH concentration of, I have it written down, right? 3.16 times 10 to the negative 3. So now we know the OH concentration, which is helpful because the OH concentration is going to be equal to the NH4 concentration, right? They're equal to each other. So if I know one, I know the other. So now I can start plugging in stuff into the Kb expression. I got this 3.16 times 10 to the minus 3 times the same thing again, 3.16 times 10 to the minus 3 all over. Well, they told me it started with 0.55 molar. And I would have used up the 3.16 times 10 to the minus 3. So I no longer have the same amount that I started with. I used some of it up. How much did I use up? Well, just look at how much NH4 plus or OH minus you made. Subtract that. That's how much you got left. So now it's just math. You plug it into your handy dandy calculator. You get 1.8 times 10 to the minus 5 as your final answer for the Kb of ammonia. And then there's more. 4. A 0.15 molar aqueous solution of a weak base has a pH of 8.88 and wants the Kb. So this is similar to the last problem. So we got the weak base, so the first step is we're going to have to use the pH to give us the OH minus concentration, right? So then we're going to do the Kb with the OH minus concentration and plug stuff in. So first step. All right, well, if I have pH and I want the OH minus, it's probably helpful to first do pOH. So I know the pOH equals 14 minus the 8.88, which equals, oh God, my brain. I have it written down, 5.12. Now we know, all right, well, I know pOH also has to equal negative log of the OH minus concentration. So we do a little algebra and we get 10 to the negative pOH has to equal OH minus concentration. And I do a little math right there and I get 7.59 times 10 times 10 to the minus 6. So that's my OH minus concentration. So now, well, what's my Kb expression? Now I'm on to that second step. I'm going to start using Kb. Well, for the base, it's going to be the conjugate acid, right? So I'm going to just say A plus the OH minus all over what you started with, which is what? The weak base, right? So now we got a number for OH minus, which should equal the same value of the conjugate acid, right? So it's really 7.59 times 10 to the minus 6 times itself again, so I'm just going to write squared all over. Well, the weak base that we started with was 0.15 molar, and we're going to subtract the amount that changed, which is 7.59 times 10 to the minus 6. Now, I'll let you know a little secret here. All right, when you have this huge difference between your starting concentration and how much was used, you can ignore how much was used up, because if you do 0.15, which is, you know, precise to the hundredths place, and you got this number which goes back like freaking 5 decimal places, when you do that math, you're going to get 0.15 still. So you can ignore this. It's all right if you don't. It'll make your life a little easier if you do ignore it and just leave it as 0.15, because that huge difference, when you do that subtraction, you're going to get the same number. So if you can recognize that, it'll save you a little bit of grief and you'll still get the right answer. You'll still get the right same number, because when you do that subtraction, it doesn't make a difference. So now we just plug and chug and we get a value of 3.84 times 10 to the minus 10. So again, when you have that huge difference, you can ignore it, because when you do the subtraction and you round to the least precise measurement, it's going to be the same number. All right, 5. What is the pH of a 0.35 molar aqueous solution of CH3NH2, which is methylamine, and Kb is 4.4 times 10 to the minus 4. Interesting. So they want the pH. So let's work backwards. Well, if I want the pH, I'm going to have to get the H plus concentration, right? All right. Well, how can I get the H plus concentration if they gave me the Kb? Interesting. Well, I know if I'm working with a base, if I know how much OH minus I got, I can figure out how much H plus I got, right? Or if I got the pOH, I could get the pH that way too. There's a couple of ways to do it, right? So in order to do that, that's when we're going to need the Kb to give us the OH minus. So we multiple step problem here. All right, so let's start with what we can. Let's just figure out, all right, well, methylamine, BCH3NH2 plus water is going to give me CH3NH3 plus OH minus. So I know my Kb expression is going to be CH3NH3 plus times OH minus concentration all over the concentration of CH3NH2. All right. So let's think about this real quick. I'll even write out, I know I've been cheating a little bit and jumping through this icebox part, but it's saying we started with 0.35 molar CH3NH2. We started with 0 of this stuff and 0 of OH minus. So the change is going to be, well, we use up X amount and we make X amount of the other things. So the equilibrium amount will be 0.35 minus X, X, and X. So now we can plug these into our Kb expression. So we get Kb equals, well, it's X times X all over 0.35 minus X. All right, so that's not too bad. So now we combine like terms, we should get it into like quadratic setup, and we're going to get X squared plus Kb X minus 0.35 Kb. Right? I haven't used numbers yet because numbers are a pain in the butt. There's so many of them. Right? So now I can use my quadratic equation of negative b plus or minus square root of b squared minus 4ac, which is all over 2a. And I get my value for x that makes sense. And I get x equals 0.0122. So what is that value? Well, that value is the same thing as my OH minus concentration. So now you can do, there's two ways to do this. You can go, well, since I got my OH minus, let me get my POH and figure out my pH from that. Or you can go, hey, if I know my OH minus, let me figure out my H plus, so then I can solve for pH that way. I prefer to use the POH to pH. So I just go, all right, well, let me figure out what the POH is. The negative log of that number. And I get POH of 1.91. But I'm not done because it wants a pH. So I got to remember that pH equals 14 minus the POH, which is that 1.91, and I get a final answer of 12.09. Bam. All right. So that's how you do that. Everybody's loving these problems, I bet. 6. An aqueous solution contains 0.05 molar methylamine. Concentration H plus in solution is blank. Molar. Kb for methylamine is given again. Boy, hey, let's figure this out again. So we're going to have to go, all right, well, methylamine, which I'm going to abbreviate MA because I'm lazy. It's acting as a base, so I got to add water to it. Plus H2O liquid gives me methylamine with an H plus and OH minus. So the Kb is going to be the methylamine conjugate acid times the OH minus concentration all over the amount of methylamine that I started with, or methylamine that's left. All right, well, I'm going to quick skip the icebox step and just go, all right, well, I know I'm going to make X amount of conjugate acid and X amount of OH minus, and it's all going to be over the amount that I started with minus the amount that got used up. So now I'm going to do, combine like terms, distribute. I'm going to get it into the ax squared plus bx plus c format, which is just some algebra, right? It's just algebra. So I'm going to get x squared plus kb x minus 0.050 kb. And I know what kb is, so I can plug in the numbers and stuff and get my a, my b, and my c values so that I can plug it into my quadratic equation. Negative b plus or minus square root of b squared minus 4ac all over 2a. And I'm going to get one x value that makes sense. And it is going to be 0.00448. Right? So that is my concentration of OH minus. that's not quite what they wanted. They wanted the concentration of H+. So now we're going to have to do a little math. So we know that, well, Kw is 10 to the minus 14, which equals concentration of H plus times OH minus, and I know OH minus, so when I rearrange this, concentration of H plus equals 10 to the minus 14 all over 0.00448, and you get 2.23 times 10 to the minus 12. So none of those things are the right answer. None of them right. Kind of a close one here, right? If you're like, oh, did I mess up somewhere? Nope, it's just none of the above, unless I made a mistake, in which case you can make fun of me in class and point it out and tell me how stupid I am. All right, 7. The base dissociation constant of ethylamine is this number. What is the H plus concentration and a concentration of that for ethylamine? All right, so first thing that we're going to want to do is figure out, well, Kb, right? Because they gave us the Kb, so what's the expression? Well, I'm just going to use a generic one. Ethylamine, it's a base, so I'm going to say that it's the H with the base, it's conjugate acid plus OH minus, times OH minus all over the amount of base that we have still. And, well, I also know values for those, right? Well, not really, but I can say they're X, so it's really going to be X amount times X, because I'm going to get the same amount of conjugate acid as I do the OH minus all over the amount that I started with, which they tell me is right here, 1.6 times 10 to the minus 2, minus the amount that was used up, X. And so now, again, I'm going to combine like terms, do a little algebra. It's just algebra. I'm going to rearrange it so that I get, quadratic setup for a polynomial thing. I'm going to get x squared plus kb times x minus the 1.6 times 10 to the minus 2 kb. Right, so plug it into my quadratic equation. I'm going to use the one value of x that makes sense, and I get x equals 2.9 times 10 to the minus 3. All right, well, what was that the concentration of? That was the concentration of the OH minus. All right, what are they asking for? What is the concentration of the H plus? So now I'm going to have to go and do one more step. Well, I know that Kw equals the H plus concentration times the OH minus concentration, and that has to equal 10 to the minus 14. So again, I rearrange to solve for H plus equals 10 to the minus 14 all over that 2.9 times 10 to the minus 3, which equals 3.45 times 10 to the minus 12. That's my final answer. And that's it. See you in class.